Saxon's Calculus Lesson 59 is about concavity and inflection points and then applications of the second derivative. So in part A, they talk about three different possibilities, and they're listing them as A, B, and C on page 293. So if you have a point at the bottom of a swoop, and they're calling that point P, that is, all points on the graph near that point P lie above the tangent line. So the tangent line would be like here, so they're lying above it. Then the graph moves up and away from the tangent line on both sides of P. We say that that is a concave up, all right, because it's forming a cave upward. Part B, all points on the graph near the point of tangency P lie below the tangent line, so that's going to a swoop, and here's your point of tangency, and they're all below that. Then the graph moves down and away from the tangent line on both sides of point P. I should label that. Then it is a concave downward. Okay, it's kind of intuitive that looks like what we're calling it. And point C, the points of the graph near the point of tangency P are above the tangent line on one side and below on the other. So their curve was something like that, and then their point of tangency was here. So on this side, it's forming a concave down, and on this side, it's forming concave up. And so, point P, label it. Thus, the curve moves up and away, concave upward on one side, and up and away, concave downward on the other side. We call this one an inflection point because two different things are happening. One concave up, one concave down. Then they show you another set of pictures on 294 of the same concave up, concave down inflection point. And then in example 1, which I've already gone ahead and put here, they say, shown is the graph of F. Indicate if the graph appears to have positive or negative concavity or has an inflection point at each of the points labeled. So at A, it's climbing, but that's making it negative. The same thing at B. At C, I'm going down and up, which is making it an inflection point. At D, I'm beginning to form concave up, so it's going to be positive. I guess the other thing I should have said here is that these are part of a concave down, and so therefore they're negative. And then this one is part of concave up, so it's positive. E is, again, I'm doing both, so inflection point, and then F is part of that concave down. It just didn't finish it, and so it's going to be negative. Now in part B, they do the geometric meaning of the second derivative. So if we differentiate the first derivative of a function, we get another function that we would call the second derivative. The value of the second derivative equals the rate of change of the first derivative. So this, we'll get to some application points and why it's important, but just realize that when you do a derivative two different times on the same equation, what you're getting is the rate of change. So then in the bold, they say if the second derivative is positive at a certain point, the slope of the graph of the function is increasing as it moves to the right, and the graph will concave upward at that point. So the second derivative can also help us understand the concave up or down, and that's why they went over that before doing this part B. Top of page 295, they show you a picture of that. And then they say, if the second derivative is negative at a certain point, the slope of the graph of the function is decreasing as the x dot moves to the right, and the graph will concave downward. So if the second derivative is positive, and they do this little smiley face thing to help you memorize this, which is kind of cute. So the eyeballs are acting as the first derivative, second derivative. So if both are positive, then the F double prime means that you are curving up making the smile. And then if the second prime is negative for both, the second one is negative, then it is frowning and it's concave down. Now that you kind of know that, they also tell you at the bottom of 295, the first derivative tells whether the slope is positive, negative, or zero, and tells us how steep the slope is if it's not zero. And then they go through some examples like 1/3 x, 2x, negative 1/3 x, negative 2x. So then on the top of 296, they show you your slope of 1/3 is a rise of 1, run of 3, but a slope of 2 is a rise of 2, run of 1. So it's much steeper if you picture that. So going over 3, up 1 is smaller than going up 2 and only over 1. That's much steeper. And then, of course, the negatives would be flipping the direction of those lines. If the second derivative is not 0 for a value of x, its value tells us whether the slope is increasing positively or negatively, and tells us how fast the slope is increasing, which is the measure of the bend in the graph at the value of x. Ooh, now that we've covered all of that lovely wordiness, let's look at example 2. At which of the points labeled on the graph is, and I'm going to pause it here while I graph. So I graphed it, and then it says, and I want you to see this formatting here, d2y over dx squared is the way they're asking for the second derivative, because here the derivative is squared, but here the x is squared. So in this graph, at which points labeled is it positive? So we are looking for a positive being places that are concave upward. So here it's concave down, but here I'm getting concave up with the points C and D. So you can see how the second derivative can help me figure out the curvatures there. Now, part C says first and second derivative tests. Now, in the box that they put on page 297, they are giving you the important things here. So for the first derivative test, and I'm going to read them and try to explain them. If the first derivative of f equals 0, sorry, it was already wordy. Okay, so if the first derivative equals 0, then the derivative of f, the slope of the graph of f is what that means, is positive for all values of x just to the left of c and negative for all values of x to the right of c. You have a local maximum. So again, now that you see the picture, if it is negative on this side and positive on the other side, you have a local max. Part 2, if the derivative of f of x, talking about the slope, is negative, then just to the left of c and positive for all values to the right, then you have a local minimum. And 3, if the derivative of f of x, the slope, has the same sign for all the values of x to the left and right, then it is an inflection point for that graph. They show you the possibilities. No, I think you've got it. If the okay, now at the bottom of 297, they begin to talk about the second derivative. If the value of the second derivative is positive or negative, then the second derivative test can be used to obtain the requirement for checking the value of the first derivative. In other words, they're kind of working backwards. So now on the top of 298, you have the second derivative test rules. If the first derivative of f of x equals 0, if the second, okay, so step 1 and step 2, if the second derivative is negative when it is not, okay, they're giving it math symbols. Then it is a local maximum value, as you see here with the frowny face. If the second derivative is positive, then you're going to have a local minimum, as you see with the smiley face. Note, a zero value in the second derivative does not necessarily tell you you have an inflection point. A zero value in the second derivative tells you to go back and use the first derivative test. Okay, so example 3. Suppose f is a polynomial function and f prime of 3 equals 0 and f double prime of 3 equals 3. Sketch the graph of the original function close to 3 and indicate if you've got a max or a min there. Okay. Since they want the sketch and we're dealing with at 3, so in the original one, 3 gave me a slope of 0, so I have a dot somewhere. I've got a straight slope here, so I know I need to be curving. Now, what did the second one tell me? I got a 3. Well, that's a positive, so it's caving up. So my rough sketch creates a parabola, and that would give me then a minimum point. Example 4. Suppose the f is a polynomial function so that f prime of 3 gives me 0, same thing I had before, and f double prime of 3 now this time gives me 0. In addition, the original derivative is positive, so f1 is positive near 3. Sketch the graph of near 3 and indicate if I have a significant point. Alrighty, so here's our 3. I've got a dot somewhere at 3. My original slope was still touching their straight line, and then this one, okay, so I don't know whether I have an inflection point or not because my second derivative test didn't help me. So then it said go back to the first derivative test where close to the 3 I was getting positives. That indicates to me not two different things, so I have to have an inflection point. So I've got to be swooping through that place. Example 5. Given f of x is x to the 4th, use the first derivative and second derivative to describe the graph near 0. Okay, I was debating if I wanted to graph it or not. All right, so I'm near 0 where we're talking about things. So the first derivative would give us 4x cubed. So when I plug in positives, I'm getting positives. When I plug in negatives, I'm getting negatives. Second derivative would give me 12x squared. If I plug in positives, I get positives. If I plug in negatives, I also get positives. So I should be... Yeah, I was double checking. Okay, so... and not at 0. Oh, I didn't test 0. 0. Oh, 0 gives me 0 no matter what is happening. So 0, 0 is definitely my point of start. And then one side is positive, one side is negative. Then I'm parabola up. And according to two positives, I'm also curving up. Yes. And it's concave up. Yep. So then describe the graph near 0. So that would be a minimum point. I think that's all they want us to do.